Hello and welcome to SDN Tech Forum. Today we are going to talk about a technology which we all are using every day without paying much attention or heed to it. That is called GPS or Global Positioning System. And why we are looking into GPS? Because this is IoT series. Previously on my channel, you have seen we have done a lot of IoT videos starting from sensors, actuator, all the way to the cloud, right? And GPS is another addition to that series. So as always, first what we want to do, we want to learn about technology, and then we will dissect the technology and see how we can build something on our own, right? So coming back to GPS, what we have in agenda. First of all, we will understand why location tracking. Then we will understand what enable location tracking. That means satellite communication. I'll touch base on high level how it works. Then we will see various navigation standard across the world like GPS, GLONASS, and finally we will do a demo where I'm going to use a USB dongle which has a GPS chip installed on inside it, and we will run some coverage test cases, or we will see how we can um, track location ourselves. Okay, sounds good. Get excited. So why location tracking? GPS provide accurate measurement of several parameters, most importantly longitude, latitude, exact time, and altitude, right? So if you don't understand longitude, latitude, these are like a your coordinates, location coordinate. Don't worry about that. We are going to talk about that in next slide. Above information, once you have those piece of information, it unlocks several use cases. Some of the use cases are your urban navigation. When you start your day and drive to office or school, right? Pretty much all the time we are or a coffee shop, pretty much every time we are going to use GPS. Then health and fitness tracker, mountain terrain coverage where there is no cellular and wired communication. That time you can use satellite communication. And within transportation, like the fleets of buses and trucks, they heavily use GPS tracking. All right. So what enables GPS? Satellite communication. That is the key to GPS technology. Satellite communication has evolved significantly in recent years. That means now we have not just the stationary satellite, but we have various type of satellite sitting very close to Earth orbit. That is one of that type is LEO or low Earth orbit satellite, which orbit closer to the Earth than other satellite and offer more accurate location. Since it is sitting very close to Earth, that means the latency is less and accuracy is higher. Another type of uh, satellite is medium Earth orbit satellite, which operate at higher altitude and provide broader coverage than LEO. And finally, there is geostationary Earth orbit satellite or geosatellite, which orbit at the same speed as Earth rotation and offer continuous coverage over a specific region. So this is moving at the same speed with Earth's orbit and have one fixed location coverage. Each type of satellite technology has its advantage and disadvantage. It has its own use cases. For example, LEO provide greater accuracy but require more number of satellite to cover the area. MEO satellite offer broader coverage but are less accurate. So dense the ring, more accuracy, sparse the ring, accuracy is less but coverage is more. And GEO offer continuous coverage but are expensive to launch and maintain. All right, so let's go to uh, GPS technology and how locations are identified. GPS technology is a system of satellite, obviously, ground station and receivers. So, namely, three component. You have your satellite itself, then you have receiver, the handheld devices like our mobile phone who are receiving these signals, and then of base station, ground base station. The GPS receiver in a device receives signal from multiple satellite and use triangulation method uh, to determine user's location. So one satellite signal alone cannot give you precise location. It need minimum two satellite to give you pinpoint a location. So it make a triangle. and we can add fourth satellite for time accuracy. This technology has revolutionized navigation and has made it possible to accurately navigate both on land and at sea. Since satellites are uh, in the Earth's orbit, so doesn't matter whether you are tracking location on ground or on sea, it works everywhere. Locations are identified through combination of latitude and longitude coordinate, which are determined by GPS receiver. These coordinate can be used to pinpoint a location on a map or provide direction to that location. Right? That's why we use GPS. So let's now understand. Now, so we know how satellite communication enables GPS services and how GPS uses triangulation to figure out your location using those coordinate. Now let's see what are the different GPS technologies available all across the world. So to start with, in United States we have GPS, which is Global Positioning System, and it was first introduced in 1970 for military uses, but then it was made available for commercial use or civilian use in 1980s. Today, GPS is widely used in United States for navigation and location-based services, and in GPS we have 30 satellite orbiting. For GPS, there are multiple band of communication. GPS work by using network of satellite orbiting the Earth to determine user location. There are two primary frequency used by GPS, L1 and L2. They're called bands. L1 operate at 1575.42 megahertz and it is used for civilian purposes, while L2 operates at 1227 megahertz and it is reserved for military use. GPS standard include L1C, L2C, L5 band, and those new band they provide higher accuracy and help you work with other global navigation satellite system um, like GLONASS and GNSS. So compared to GPS, there is another prominent system called GLONASS. GLONASS, which stands for Global Navigation Satellite System, was introduced by Soviet Union, now Russia, in 1982 as a response to American GPS system. It consists of constellation of satellites that orbit the Earth at an altitude of approximately 19,000 kilometers. The system is operated by Russian Aerospace Defense, and in 2021, GLONASS has total 24 active satellite in its constellation with 3 additional satellite in reserve. You always have a couple of satellite in reserve because if one fails, you don't have to wait for the launch. You can simply add the standby. Other than GPS and GLONASS, there are other navigation system established by other countries. Like in Europe, we have Galileo, and it is still being deployed, and today it has almost 30 satellite in orbit. India is developing its own GPS system called Navik, navigation with Indian constellation, and it will unlock regional use cases. I think it's going to have 7 satellite by the time the deployment is completed. China invested heavily in developing its own GPS system called Baidu, that is Big Dipper in Chinese, and it is made up both satellite and ground station, and yeah, coming up with its own satellite system. Japan also developing a regional navigation system called Quasi Zenith Satellite System. QZSS is regional system that is designed to improve accuracy and availability of GPS in Japan. So while all the countries they are developing their own system, it's not like GPS or GLONASS or Galileo is being used by their by United States and uh, Europe only, right? All this GPS system they are available for all other countries. So GPS like uh, which was developed in United States is really popular and available pretty much all across the world. So now it is time to talk about now so we know how the technology work and the standards. Now it is time to talk about what we are going to do. So for this this workshop, I have procured this module. This is an inexpensive module, and as you can see, it says GPS and GLONASS. That means it can support those two navigation system, but it has a GPS chip inside this, which is interfacing with a uh, USB output. So this is a USB GPS module. GPS GLONASS supports GPS and GLONASS. This USB GPS module work with Windows, Mac, Linux, Android, Raspberry Pi, and other some of the car as well. So this chip is really compatible. This unit transmit data in NMEA format. And if you are not sure what is NMEA format, I'll talk about that. NMEA is a data serialization standard. This chip or this USB is plug and play for Linux system. For Windows system, you may have to download and install a driver. Also, the refresh rate, as per specification, it's 10 hertz. That means it can get 10 update per second. It is also a plug and play. So when you plug it to a Raspberry Pi or a Linux machine, you will see that it is straightforward detected as TTY line ACMO, ACM0. And then there is a link which talk about all NMEA standard. While you don't want to go and read that website, so here is a snippet of what is NMEA 0183 standard. So our USB chip supports NMEA 0183 standard. And what is that? As you can see, is used worldwide across many industry segments. The standard defined electrical signal requirement, data transmission protocol, and time and specific sequence format for 4800 baud serial data bus. So basically, all the data when serialized, and it can directly go to your TTY line. Each bus may have only one talker but many listener. This standard is intended to support one-way serial data transmission. So now at this point of time, what we are going to do, we are going to connect the USB dongle to a Raspberry Pi, and I'll advise you connect using a long USB cable. That means you have USB to USB converter, and try to keep your dongle a little far from Raspberry Pi instead of directly attaching to Raspberry Pi, because this dongle try to acquire GPS signal, and Raspberry Pi in turn generate a lot of interference in terms of noise, signal to noise ratio. So it's better to separate them using a long USB to USB cable. So once we have that installed, what we are going to do, we are going to use inbuilt command line or a program called GPS monitoring dash n. Don't resolve the name, etc. And once you do that, if your Raspberry Pi has already detected the device, it will generate an output. It will try to capture um, the satellite signal. And once it captures the satellite signal, these are the information what we are going to see on our screen. So I'm dissecting that here, but I'll show you a real demo as well. When you do GPS mon, assuming satellite signal is acquired, these are the things you're going to see. You're going to see time, what is the current time looks like, what is the latitude information, longitude information, what is your altitude, then the speed and heading, which direction you are heading, satellite, how many satellite this GPS dongle can see, HDOP horizontal dilution, VDOP vertical dilution, and PPS pulses per second synchronization is enabled. So not all chips can give you all the information like PPS and HDOP and VDOP, but every GPS should give you at least this information: time, latitude, and longitude. So this is now time to head on to our demo setup. Okay, for that I am logged into my Raspberry Pi, And from here, what we can going to do is check if my device is detected. And I'm going to just grab with AC. So as you can see, we have this dongle connected and it is detected as TTYACM0, right? So now how to run this GPS mon? Or can we run GPS mon right away? TCP device open cannot connect host and pair, right? So you have to mount it actually, because right now if I show you, we are not listening to any particular port, right? This is a serial data that doesn't ride on IP address and a port at that TCP IP layer. It is a serial data. So for that, what you have to do, you have to actually mount this. And here is a link to Git repo. Yes, and this is the gist. So there are a couple of things you can find here. The first one is GPS module install. I already shown you that we have the GPS device detected, and now what you have to do, you have to just mount it using this command. Once we do that, we are ready to run GPS mon-n. And as you can see, it is listening on local host on certain port and dev TTY CM0. And this is NMEA 083 standard. So serialized data is uh, sent directly to the host, right? And this is our um, GPS information. You can see we have time set up here, we have latitude, longitude, speed, and magnetic variation, and all those things, HDOP, GOID, so much of information, right? And here also you can see there are a lot of satellite responses. All these are talker ID, and they are getting response from various satellites. So what you can do, you can decode or understand it yourself, but that is kind of time consuming, right? So there are some programs available, freeware programs available, which can help you decode this data and show you pretty easily, right? So what you can do, you can take this output as some of the format, say GPX format, import it in Google Earth, and it can show you a nice chart. However, we would like to understand what is the output. So for that, let's go and spend some time decoding the output, or the things what we have seen on our screen, right? So decoding NMEA output, and I have taken a sample of this talker ID. Say we are going to pick any one of these from here, say GPA RMC, and try to decode this, that what does this mean? What is the information we are getting from this satellite? So for that, if you see, I have a sample here, GPMRC, and then the complete line. The decode information given from GPMRC RMC sentence is as follow. The first is time, 1959 12.00. This is coordinated universal time or epoch time. So if you go to epoch converter and try to convert this, you will see that it will be converted as a human readable time. Right now it's a decimal, doesn't make much sense, but it will be converted 1959 12. Let me try that. 1959 12. So as you can see, it date back to 1970. That is the Unix times, Unix start of time, right? So we are not getting correct Unix epoch time because this is the right current time. All right. So first is uh, time information, which is not correct, but that's fine. Then status A is for active. That means we are actively receiving the signal. And then we have latitude 3550 dot something north, and this is longitude 07854 dot something west, right? And how to read this? You can read this something like this. So the first two digit is degree, and then rest of them are in minute. So 35 degree 50.22 minute north, 78 degree 54,622 west, minute west. Okay, and this is my speed. So this is speed in knots, and then this is course over ground, and date is again here. So we have a date as well, and magnetic variation 9.1 degree west, checksum. Okay, so this is how you can decode, or at least you know what is the information coming, right? It's not Greek to you. Okay, now you can see while this is running, let's go and see what else we can do here. So one important thing you can see right now in output, we have information coming from a lot of satellite, right? Not just from GPS, but GLONASS and maybe Galileo as well. So what you can do to control the response, whether you want to receive data from only from GNSS or not from GPS, what you can use NEMA sentences and filter based on that. Because so how you can filter? You can see that NEMA sentences, each sentence start with a talker ID followed by sentence identifier. That's where you can see GP is for GPS and GN is for GNSS. So you can filter based on that. You can apply some regex and make sure that you have only GP because you want to read through the GPS satellite only. Right. So that's a one quick trick. Coordinate decimal conversion. So when you go to coordinate, when you want to resolve the coordinate to a street address or a location, you need to know the decimal value of it. Right now, my GPS mon is giving me data in this format, right? 35 degree 50 something to north. So you need to convert it in decimal before you can use it in some program, say Google Earth or anywhere. How to do that? For example, say 3550, if I have to convert this in decimal value, this is the formula. 35, that's degree, plus 50 and whatever is in minute, divided by 60, that's your seconds, right? And then whatever comes is your decimal coordinate. For the same thing, you can do the same here. Here you can see 78 and then 54 divided by this. So it gives you a degree coordinate. Sorry about that. So how you can save the output data while I have the data running? Uh, what are the different formats I can save it, right? Um, there is one prominent standard which is GPX, GPS exchange format, is widely used XML based file system for storing GPS data. Because as you can see, I have my GPS running, but this data doesn't make much sense right now, right? How I can use pieces of information and build it into an application. So for that, I need to save it somewhere, and to and for output, there are various standard which go along with application development, and one of them is GPX, which is XML based file format. Then we have KML, keyhole markup language, is used for displaying geography data in mapping applications such as Google Earth. CSV, for us, we are going to save it as a CSV uh, so that all the latitude and longitude are captured in different columns, and we can take those column value and draw it on a map like Google Map. Another is TCX, Training Center XML. TCX is again XML based file format commonly used for storing fitness related GPS data such as recorded workout and activities. FIT, this is fit Fitbit or Garmin devices. And then we have OSM, which is OpenStreetMap. OSM is open data format used for collaborative mapping. This is useful for contributing GPS track to OpenStreetMap. OpenStreetMap is like open source initiative for a just like Google Map. All right. And let's take one of the double click into one of the standard, and GPX is really popular. So what GPX has, it has a waypoint, it has tracks, it has routes, and these are the things which you will need while you are developing your application, right? So for example, waypoint include information such as latitude, longitude, or possibly additional metadata like name, description, elevation, etc. Right. So it has all those attributes which can help you uh, deploy your application or develop your application faster. And this is my attempt to decode things with ChatGPT, right? Because when we are talking IoT, we cannot, or any other topic, we cannot escape AI. So I wanted to decode it. Obviously, there are certain programs which you need to install, but I just asked ChatGPT, can you decode these values for me, like what I'm getting here, simply copy and paste. And ChatGPT is clever enough or intelligent enough to decode each NEMA sentence. And as you can see, we have time, latitude, longitude for GPRMC, similar to GPGSA, and so on. All those were decoded thanks to ChatGPT. All right. So I hope you feel confident and you're excited to do some of the GPS hands-on uh, of your own. And if you happen to procure a GPS chip, you may use this gist to mount it and start using your GPS one. Also, I would like to show you there is a script. So instead of running and displaying thing on your screen, what you can do, you can run a script like this, where I'm saying that run GPS CSV, which is another program, every minute, take a 60-second of sleep. So sleep for run this thing, take 60-second sleep, and while you do that, save the output to my data file, outside data file. And this data file will have all the longitude, latitude in the column. You can take that, sanitize that a little bit, and then what you can do, you can go to programs like Google Map and create your own map. As you can see, I have imported my table. So what I did, I have this battery powered Raspberry Pi, and I connected this GPS dongle and took it for a ride, on a bicycle ride, say, because car may be moving really fast and it's close, so you may not get signal. I decided to take it on a bicycle ride, and then while I was riding, the GPS program was running, because GPS program doesn't need any kind of Wi-Fi or cellular connection, right? It is running on a um, serial port. So as long as your CPU is running, it's fine, right? So I got the data and then I sanitized that. That means I have only latitude and longitude information, and simply I can draw it on a Google map. So as you can see, all these locations, they are coming from my CSV file. All right, so pretty exciting. I'm really excited to continue my work or prototyping with GPS. And if this is something excites you, you procure some chip and start playing with this, please feel free to write me in the comment section. And if you have any questions, queries, feel free to reach out. Thank you very much, and see you in next video.